This call is now being recorded.
Yeah, okay. So for those who were not here, so we've been doing questions lately, right? So we're doing exam questions actually for, so last time we met, we were doing for Newton's laws, the laws of motion. So today we carry on. We will be doing the work, energy, and power, right? So yeah, let's get to it. So just we see and we know how to deal with these, because very soon you will be writing your preliminary exams. So let's start. Can everyone see my screen? Okay, just give me a thumbs up if you can see my screen, then I can start working. Cool, thank you. So let's start here. We're looking at 2022 November question paper. So we're doing the work, energy, and power aspect of it. So here they are talking about a 12 kg block initially at rest. We should note down some of the keywords that we see as we read our question here. So it's at rest at point A at the bottom of a rough inclined plane. Okay. And then the block is pulled up the incline by a constant force F acting parallel to the incline, which is fine. Then the block reaches point B. This is point B here, which is vertically, which is at a vertical height of 4.5 meters above horizontal, with a speed of 2.25. Very important, right? So let's start. Question 5.1. What they want from you here is the definition of a non-conservative force. So, does anyone know what is conservative force? Anyone? A non-conservative force, right? So now, I'm going to give you a definition for this. So you should actually check it on your exam guideline so that you write it the way they want it, because there's a certain keywords that they want from this, right? So this is a force. So a force is a non-conservative force if work done, if the work done by this force, the force, right? So we're talking about work here. So if the work done by this force on an object, right? So on an object, so work is done. We know that work is done when an object moves between 2 points, right? On an object. So I can add for you here and say, remember, work moves, it's done on an object. That has displacement, right? So which by the force on an object, right, depends on the path taken, right? So let me just say here, let me use this one, depends on the path taken, right? So if I were to show you work, this is work done is force times displacement, which is the 2 points, cos theta. right? So I've taught this before that this is the force here. This is the displacement, right? This is the displacement. Then this is angle between force and the surface, right? So the angle between this force F and this surface here, that is our theta, right? So your displacement would be something like, if we move from here to point B, then we would get our displacement, okay? Or moving from point A, because so it's actually at rest at here, point A. So if it moves till here, then we can have a displacement, right? Okay, cool. Then we can move to, does anyone understand before I move? Because let's say here in this case, if this becomes 0, that means there is no movement. If this is 0, and then there is no work done, right? If the force is also 0, then there's also no work done, right? So this is how it works. So 5.2. Let's look at 5.2. What is, so they're asking us here to draw a labeled free body diagram for the block when it is pulled up the incline. So the block is no longer here, it's being pulled. Let's assume it's here. So now they want a free body diagram for that. So as we know it, free body diagram up the incline. So let me just draw some dashed lines so that you see. We remember that when you draw a free body diagram, you put a dot here. Okay. So now that you've put your dot, first force can be any force that you want to start with. This is gonna be your normal force, right? So they're gonna ask you what is a normal force. The same way they're asking you what is a non-conservative force. Sometimes they might just want this one. Sometimes when you're in the Newton's questions, they might want a normal force, a frictional force, those kinds of things. So you should know these definitions. It's just 2 marks for free. Okay. So now we have this normal force here. We have our F that was given to us. Then we have weight, which is Fg, right? And I have taught here that the minute they tell you about the rough surface, so this is a rough inclined plane, that means there is friction here. So what they are saying to you, this surface here is not smooth. So there is friction that is stopping or trying to stop the box from moving. So therefore, you would have your frictional force here, which is, let's say, Fk, this instance, right? That is your frictional force. So you've got 4 marks here. So with these 4 marks, you've got 4 forces. So alternatively, you can write this in terms of your components here. Do we all know components? Your Fg perpendicular and your Fg parallel. These are very important. But now, the minute you put these components, then you wouldn't have to put this Fg here. Okay? Do you understand? Okay. So let's move to the next question. Just copy, then put it here. Okay, so now an interesting question. They want calculate the total work done on the block by non-conservative forces when the block moved from point A to point B. So like there are different ways of doing this. Okay, different ways. I'm not sure which one you prefer, but for now, let's use this one. So 5.3. 5.3. So here they want total work done. So we want work net here. So one would do this. One would use this free body diagram and calculate the forces, right? And calculate the forces here. But it's a long route. So let's use what we know, right? So there is this rule here that says work which is done by non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. Let me just say P here. Right, we have seen this. I'm sure you've seen it. Maybe also the back of your question paper, they might give it to you. But this is how it looks. So remember, kinetic energy, EK, is equals to 1 over 2 mass times velocity squared. Then potential energy is equals to mass times gravitational acceleration times height. So here, this is your 9.8 meters per second squared. Okay, then these are your masses. So now we've got the mass of the box, we've got the final here. This is the final velocity. We have it. So here, let's calculate this part first. So we're gonna calculate these parts one by one. Let's start with the change in kinetic energy. So what this is saying kinetic energy, final kinetic energy minus initial kinetic energy, right? This is what it's telling you. So you can do it like so. So the 1 over 2 mvf, which is mv final squared, minus 1 over 2 mv initial squared. This is your change in kinetic energy. Okay, so this is how you go with it. EK. So here we have the mass already, which is fine. Say, so now the question said that initially it was at rest. So that means the velocity is 0 meters per second, not per second square, because it's not acceleration. Then final is given to us, which is 2.25 meters per second, right? So that means we've already got most of the things that we are looking for, actually. So that means if we carry on, we can say change in kinetic energy equals to 1 over 2. Our mass is 12 kg here. Then this is 12. This is 12. VF we've been given, which is 2.25, then squared, right? Minus 1 over 2, 12. Initially, it was 0. At point A, it was 0. So it's going to be 0 here. Okay? So you've got your change in kinetic energy here. Can someone please punch in the calculator? And then we see what's the answer here. Anyone? Okay, so you'd have something like 30.375 joules, which is your energy. And then we did with the second part, which is our potential energy here. So potential energy, which is our change in potential energy. Change in potential energy, which is equals to mg h final minus mg h initial, right? So that is this height here. Okay, so mass again is 12 times 9.8 times our height is 4.5, right? Minus. When it was here, the height was 0. So you can say 12, 9.8 all times 0. Okay. And then you would end up with your potential energy here. So your potential energy is going to be 9.8 times 4.5. It's all in meters. So we don't need to worry. So we'd have 5 to 9.2 joules. Okay. So now that we are here, we just need to take this part here, and add it with this part, which gives us this part here, which is our work done, right? So moving to the next, we come here, let's paste it again. So that means work done by non-conservative force equals to the change in kinetic energy plus the change in potential energy. And we've already got the values for this. So it's going to be 30.327, is it? Or 75 actually. 75 plus, this is 529.2. 529.2. So that means this is going to be your work done. So you should visit this if you don't understand. So there's 29.2. Okay, let me start afresh. 0.5 plus 529.2. So you're gonna have your 559.575 joules, right? This is your answer, as your final answer. So you should visit. We've got the notes. I think I uploaded them. We've also got the video where we cover this. So you can go back there and just check out the video. Then it will be very helpful. Okay. Someone said they can't see the screen. Oh, they left. Okay. Cool. No problem. So let's move to 5.4. So do we understand so far? Give me a thumbs up if we understand. Okay, cool. So we're gonna move to 5.4. So 5.4 here, they're saying the same constant force now moves the block at a constant speed or constant velocity here, which is very important, across a horizontal rough surface from point B to point C. So let's say point C is here. So we can just put point C here. So now that means the box, or actually this is the one here, right? So the box is being pulled horizontally now, right? So they are saying now, force Fx parallel to the horizontal surface, which is fine. The magnitude of the constant frictional force acting on the block while moving from point B to point C is 42 newtons larger, right, than the magnitude of the constant frictional force acting on block when it was moving from point A to point B, right? Then they ask you to calculate the distance between point A and point B. So the way this question is structured to confuse you, right? So it's structured to confuse you. So we're gonna try and dissolve it such that you are able to understand, right? Okay, so let's start with the work. We want the distance. We've got work net. This work net here, we know that it's the work done by non-conservative forces, right? Non-conservative forces. So how then do we calculate that? Okay, so let's start. So we know that this work, let's start with work done by non-conservative forces. We've already found it. Then 5,575 joules. So we know our conservative forces. They've given us, we've got friction, and then we've got the applied force as our non-conservative forces. Please also check this on your exam guidelines there. So now we can actually say work net is equals to the work done by friction plus the work done by our force F, right? And we know that work done, work is equals to the force, whichever force might be friction or the applied force, times the displacement cos theta. Okay, so that means we're gonna come here now. So we're gonna have our force here, work net, our work net, and then times equals to the work done by force. So let's start with friction. Friction is gonna be negative because it's going to the opposite side. So it's gonna do negative work. And then x cos theta plus the work done by the force F, which is gonna be positive because it's going to the positive side, right? So therefore, what we do here, we don't have our what you call this thing. Where is it? Our frictional force, right? It has not been given to us. Okay. So, but what we know is that the frictional force at the top is actually 42 newtons more than the one at the bottom. Okay. So let's try tackling this then, because we've got many unknowns that we need to address. So let's say 9.5, 575 plus 2. negative Fk, our displacement here, okay, cos theta plus our force displacement cos theta. Okay, then now we can work. So theta, what is our theta? So theta, we're gonna, since here we've already put negative, then we're gonna put 0. Even this side we're gonna put 0. But if we had not put this negative, then for this Fk, we're gonna put 180 degrees, which will turn this thing into negative, right? So let's go and say Fk cos 0 plus F displacement cos 0 again. So now you would have 559.575, which is equal to minus Fk displacement plus F displacement. Okay, you will understand it. So since this is the same, I can say F minus Fk all times the displacement, just factoring out the displacement. Okay, do you understand? Then we can just say this is our equation 1. Okay, so now let's move. So since we already know that this here is this one on the incline, then from point B to point C, they told us that friction, which is, let me say, friction where is this friction? Let me say friction from B is gonna be friction, which is from Fk, which is this one on this side, plus 42 newtons. Because remember, they told us it's 42 newtons larger. So that means they added 42 newtons on top. Okay, this is it. So if I were to use something like the Newton's laws, again, because we know that F net equals to MA, right? Because we're on a horizontal surface. So now on this horizontal surface, they told us that constant velocity. So constant velocity means the acceleration is 0 meters per second squared, right? For the same force. So now we'd have your force, which is positive, plus minus F at B. This is your friction point B, from point B to C, which is equal to M times 0. Okay? So we're going to have your F here plus minus FB equals to 0. And we already know that is equals to this. So what we are trying to do here is to get to our equation 2 so that we can do a simultaneous equation. Because we already saw that we've got 2 unknowns. So we need a simultaneous equation to solve for them. Okay? So now we're going to have F plus, this is going to be minus Fk plus 42, right? Which is equals to 0. I can play with this now. So I can just say F minus Fk minus 42 equals to 0. Okay, so I can choose whichever that I want to choose. So I can end up with maybe something like f minus fk equals to 42. Okay, and then maybe let me just say this is my equation 2. So let's see here, what do we have? We already have this here, which is a similar thing to what we have here, right? So we can say sub in 2 into equation 1. So equation 1 is 559.575 equals to f minus fk times displacement. Okay, so that means I'm gonna take this, put it inside here. So I'm gonna have my 559.575 equals to 42 actually, sorry, times my displacement. Then to get the displacement, because that's what we want, so we're gonna divide by 42. 42 goes away, then we get our displacement here. So what is our displacement? It's gonna be 559.575 divided by 42. Then you get a number like 13.25 meters. Please don't forget, put the correct conversion, right? Okay, so let's move and try another. So if you don't understand, you can stop me. So we're going to 2024, question 5. So how we are going to work is, for each chapter, once we are done with it, we are going to do questions for the chapter, okay? So that we make sure that you understand each and everything before we pass, right? We don't want to pass stuff, but then we find that you don't understand, okay? Okay, coolies. Let's look at question 5. So question 5 here, what do they want from us? Question 5. So a constant force F is applied at an angle 30 to a horizontal on a crate of mass 6 kg, initially at rest. Very important. Initially at rest. So I think what you can do, try by all means to mark the keywords when you see them. The first time you read the question, mark these things. Then a constant frictional force of 10. Let's mark it also. Acts on a crate as it moves from rest at point A along a horizontal surface to point B. The distance between point A and point B is 1.5 meters, which is this here. And then the speed of the crate at point B is 2 meters per second. Okay? Very important. So let's start. 5.1. Work done by a force. So what is work done by a force? So we know that work equals to, this is the force, displacement, cos theta. this cos theta. So you see, this is a great example here. So you see, this is these dotted lines here. So this 30 degrees is the angle between the horizontal and the force here. This statement here is telling you what it is. So which is becomes this theta here. Okay. So how do you then? You need to define your work done, right? You need to define this work done in weights. Use your exam guidelines. Please use your exam guidelines so that you know this thing. Okay. So I won't dwell much on it. I'm gonna move. This one you can read it on your own. So we've got 5.2. So we want a leveled free body diagram showing all forces acting on the crate. So if so far this is 15 marks, this is 12 marks. So these are free marks that you should be getting, right? So these are free marks also from the Newton's laws that I've taught you. I'm not sure how many marks it was, but those are free marks that you should get. Please don't throw them away. These are free marks. So if I can check, let me see if I can find something. So what we're doing is 13 marks. So before we've got 13 marks plus these 12 marks. That is different papers. So they balance these things out. But what I'm saying is you've got the 13 marks or 15 marks. Let's say, for an example, these two questions, 15 marks each. So that means for you, you've already got the 30 marks out of 150, right? Don't lose these marks. These are free marks. These are free marks, guys, right? So draw your free body diagram. Also, this is free marks. You should not throw it away. So free body diagram as we know it, just gonna be fast on it because we know it. We're gonna have your normal force here because it's on a horizontal surface. And then even on an incline, you'd have it. So it's gonna point according to that. Then you have your force F here. Then you have your weight, which is Fg. Then you have your frictional force. Frictional force, don't forget it, they've mentioned it here, this statement here. So please don't forget it, your Fk, right? So this is how it looks bad, it doesn't look good. This is how your free body diagram would look, okay? So let's move. Use energy principles only to calculate the magnitude of F. Energy principles only. They are very specific, right? So with energy principles, let's use what we just used before, okay? Which is, let's say 5.3, which is work done by non-conservative force is equals to the change in kinetic energy plus the change in potential energy. Okay, we can easily get this. We can easily get this. So let me simplify it a bit. Gonna have work done by non-conservative force equals to 1/2. I'm just gonna simplify it. This is squared plus mg. Then we're gonna have your hf minus your hi. So this one you can write it in full, but I'm writing like this because of time, right? So this is a simplified version of it. So then what we can do is, we know that non-conservative forces that we have here, we've got this friction here. This is supposed to be Fk. Then we've got this force here, right? The same way we did on the previous question. So before I carry on, let's leave it a bit for this. Let's leave this part a bit. So now work done. Let's say work net. Work done by friction. You would have your Fk cos theta plus your F displacement cos theta. These two should be equal. Please refer to the conservation of energy, right? So you would also see it there. So this is your non-conservative forces. So cool. Then we move. We've already got this 10 here. We don't have the force. We are looking for the force, which is fine. Let's move to the next page. Let me just rewrite my stuff here. So what I'm gonna do now is this. Let me just push this up a bit. So we know we have this MC, which is equals to 1 over 2 m Vf squared minus Vi squared plus mg hf minus hi. This is final. This is initial. Final velocity, initial velocity. All right. Then I had also my work done, which is my work net. Work net, I had it as Fk displacement times cos theta plus F, which is our applied force, displacement cos theta. Okay. So now that we are here, what do we do? Okay. So the displacement, this box here, is going to move from point A to point B. That means it's going to cover 1.5 meters. This is going to be the displacement here for both of these, right? We can substitute that. Then here, this one. So here, let me just write this so that you can see them. It's going to be 1.5 meters, 1.5 meters. And then your Fk, they've also given you as 10 newtons, right? Then here, so since this box is going this side and this force is going this side, you can either put a negative here and then put a 0 here, okay? Or you can put a 180 degree here, which says, yes, the box is going this side, but that means the frictional force actually is going the opposite direction, which is 180 degrees, right? So that's how it goes. So then here, this we don't have our unknown. Then this here, remember, I said this is the angle between the surface and the force here. Okay, so that means this is gonna be 30 degrees. Okay, then let's work on this other one here. The mass, we have it, which is 6 kg. Your final velocity, they said here. So our final velocity, the speed here at point B, because now we are at point B, we've covered 1.5 meters. So our speed is gonna be 2 meters per second. Initially, here we were at rest. It is somewhere on this here. It's at rest at point A. So that means here 0 meters per second. Okay, that's why it's very important to read the statement well. Then here we still have the mass, which is 6 kg. We have g, which is our gravitational acceleration, which is 9.8 meters per second squared. But now, height, there is no height here. This thing is not moving vertically, it's not moving up and down, but instead it is moving horizontally, like so. So that means both of them are gonna be zeros. Okay, but you still need to show that you've done the work. Okay, so let's start with the first one. We have let me see, work done by non-conservative force 1/2 times 6 kg, and then you're gonna have 2 squared minus 0. Okay, plus if you substitute this, you're gonna have your 6 times 9.8, then 0 minus 0. So that means this whole thing is gonna be 0. Okay, so that means then here we have this 1/2, which is 3 times 4 plus 0. So this is 6 divided by 2 is 3. 2 squared 4. Okay, so that means it's gonna be equals to be 12 here. Okay, let's move. Then we have work net. Let me put another thingy here. So work net is equals to, we're gonna substitute by Fk, we've got 10, displacement 1.5, then cos 180. I'm gonna use 180 for now. So just like I said, if you put negative here, don't put 180 here, because it's gonna be two negatives and then it's gonna become positive and it's gonna give you a wrong answer. So then we carry on. This is 1.5. Then this one here, let me just put it here, cos 30, right? So would have work net equals to, let's punch in the calculator and see, it's gonna be 10 times 1.5, which is minus 15 here, because we're gonna say times cos 180, which is minus 15, then plus f. Then this f is gonna be, say, 1.5 times 0.5 times cos 30. The c. So it can either then say it's gonna be 1.30, like this, right? So now you've got these two equations here. You've got this here, then you've got this here. So you can do your F. So we know that NC equals to work net. Okay, work net. So that means we're gonna say 12 is equals to minus 15 plus F 1.30. Okay, so this is gonna be what you say here, 12 plus 15 equals to F.1. F times 1.30. Okay, do you see where we are going? So then you can just divide here by 1.30 by 1.30. This is gonna go away, then you should get your final answer here. Okay, Do we understand? This is gonna be 20 point, let's say 7 newtons actually. Okay, so this is how your answer would look. So the last question asks you here, it says a 2 kg object is placed inside the crate. What effect will this have on the work done by the same force F when the crate is again moved from point A to point B? Okay, so here what they are saying is instead of just 6 kg, then now we have something like this, just to say. So you can just say 2 kg here, then 6 kg outside. So we have that map. So how will this then affect the work done? Okay. So actually, if you can see the formula for work done, let's remove this. So the formula for work done says work equals to F x cos theta. So even if they put more weight or decrease the weight, it doesn't affect our formula here because we're not using any weight or any mass on this formula here. But if they had changed the displacement or the angle or the force, then our work done was going to change. So in this case, we can simply say it's going to remain the same. So usually when they ask you these questions, just take the formula for whatever that they're asking you. So for an example here, there was one that was asking about, let's say F net equals to MA, right? Not, let me use this one instead. So let me use the friction one, friction UN. So they ask, let's say again, you increase this mass here. So when you increase this mass, what will happen to friction? Is it going to decrease, increase, or remain the same? Right? So in this case, what you need to do is you need to check here. You have your normal force. So with this normal force, we know that normal force on a flat surface, if the force is not inclined, again, so we can just say our normal force is equal to mg. So that means the more I increase this mass, I actually increase the normal force. And if I increase the normal force, I'm therefore increasing the frictional force. Okay? So that's how it actually works. Okay. Done for this question. Let's see if we can find any other question here. Okay. One more question, then we can close. Let me put it here. Okay. So please also visit this. Please visit it. So this is your conservation. Okay, let me start from scratch instead. Actually, a crate of mass 18 kg initially addressed. So you see, we've done 3 questions and we can already see the pattern between these questions. Then slides down a frictionless slope, right? So now here they are removing friction from point A to point B. Okay, the crate then moves along a rough. So that means here, no friction. right? Then the minute you get here, then there is friction here because they are saying it's a rough surface, hence there is friction. So from point B to point C, point A is 3 meters above horizontal, which is this here. Okay, then the principle of conservation of mechanical energy, 5.1. What is the principle? Okay, so the principle actually in formula, I can say to you, it says the mechanical energy at the top is equals to the mechanical energy at the bottom. Hi, please mute yourself if you just joined.
Museum so good, so
Hi, patience, can you please mute yourself? Okay, let's do this. So, as I was saying, so the mechanical energy says here, the mechanical energy at the top should be equals to the mechanical energy at the bottom, right? But this is for an isolated system. So, isolated system, right? So, the mechanical energy has remained constant. Constant. Okay? Coolies. So now they are saying use energy principles only to calculate the speed of the crate at point B. Okay, let's do this. 5.2. So we can use the formula that I just defined right now, right? Because it forms part of the energy principles. So mechanical energy. What is mechanical energy? So mechanical energy is actually potential energy. Let me start with, I like with starting with kinetic energy plus potential energy here. Let me just, for consistency, use UP. So this is gonna be at the top is equals to potential kinetic energy plus potential energy at the bottom. At the bottom here, right? So we know our kinetic energy, what it is and all, right? So kinetic energy here at point A. So top is point A. So instead, maybe I can use point A instead. So that means point A, then point B, right? So what we are saying here, at point A, we have kinetic energy, which is 1 over 2. The mass of the box is 18 kg, but the velocity at point A is at rest here, initially at rest. So that means it's 0. So you can say 0 squared plus the mechanical energy now. Mechanical energy we know is mgh, right? So let me go back a bit so that you see 1 over 2 mv squared plus mgh from point A equals to 1 over 2 mv squared plus mgh at point B. Okay, so we are here now. You can say 1 over 2, 18, which is our mass, times 0 squared plus our m is 18 again times 9.8 times the height here is 3. The height between the ground and point A is 3 meters. So we can say 3 here. Okay. Okay, there we go. Hi. Okay. Thank you for muting. So let's carry on, right? So equals to, now what do we want? We want the speed of the crate at point B. So that means this is what we want here. This is what we are looking for. So we can say 1 over 2, 18 v squared plus, let me write it here, 18 times 9.8, but now we are at the bottom here. So there's no longer any height. So the height at that point is 0, right? So that means at point B, the height is 0. This is B. Okay? This is gonna be 0. This is gonna be also 0. Also 0. Then we are left now with this 18 times 9.8 times 3 equals to 1 over 2 times 18 v squared, like this. Or I can put it in this manner. Okay? Then that means from this you can get your v, which is your v squared here. So let's punch in the calculator, times 9.8 times 3. We have 529.2 equals to, this is gonna be 9 actually. So it's gonna be 9. It's gonna be 9 v squared. Then divide by 9, then goes away. The v squared equals to 529.2 divided by 9. So that is 58.8. Simply put your square root here. So now that you've put your square root, you'd end up with v being equals to square root something like 7.67 meters per second. That is your velocity at point B here. Okay? Does it make sense? Okay, we can move. So here, okay, let me copy again. Copy, put it here. So in this case, how do we then deal with the following question? Because now they are saying a constant frictional force of 40 newtons acts on a crate as it moves from point B. Remember, we said here there is friction here. Friction. So that friction, that means it's going to be 40.6 newtons here. Point B to C. Then the crate comes to rest at C. Then that means here it's going to stop again. Okay, fine. What is, state the work energy theorem? Point 3. Work energy theorem. Okay. You can state it, right? Which in simple words, it says, let me put it here. It says work net is equals to the change in the object's kinetic energy. That is what the work energy theorem says. Okay? Please know this. Know it in weights. Right? Know it in weights. So what this thing is saying is that you have work net is equals to kinetic energy, which is final, minus initial kinetic energy. Then we can do it in this manner. We can say 1 over 2 mvf squared minus 1 over 2 mvi squared, which is for initial. This is your work energy theory. So what do they want now? 5.4. Use work energy principles only to calculate the distance that the crate traveled from point B to C. Okay, from point B to C. So that means what we can do here, let's start with this. Work net, we can say work net equals to 1 over 2. So at most, you can see what they want. They also they ask you to state the principle or define something and then ask you about it, right? So now they're asking you about energy principles. So you can simply use this one, or you can go back to the mechanical energy and the work done by non-conservative forces and stuff, right? So here we can say the box is 18 kgs, but now they said at C it comes to rest. At C it comes to rest. So that means here velocity is going to be 0 minus 1 over 2, 18. Initially, let's see at B, what's the velocity at B? Did they mention it anywhere? Actually, they've asked us to calculate it here. Okay, so that means we need to fetch our 7.67 squared here. Okay, which is what we calculated. Then we can get our work net. So that is going to be 0 minus, let's go for it and see 7.67 squared times 9. This goes back to 529.46. Okay, now you've got your work net. Okay, so in this case, we can say here, check the box. The box actually has only one force acting on it, which is our non-conservative force, friction. And we know that the work net, so we can say the work done by friction, since it's the only force, is equals to work net. So that means the work done by friction equals to frictional force, the displacement, cos theta. This is going to be equals to work net because it's the only force. This is the only force. Only non-consecutive force. Right? Hence, we have that. So we already have our friction. So we can say work done by frictional force is equal to 40.6 times the displacement, which is what we are looking for. The distance traveled from B to C. This is what we're looking for. Then cos. This is going to be 180 because friction is going this way and the box is going the other way. So it's opposite to each other. or you can put a negative here. If you put a negative here, put a 0 here. Don't make the mistake of putting a negative in 180, the same place, right? So here, that means, let's move to the next page. Let's put it here. So here it means that you have your work net here, which is equal to minus 529, right? Then you have the work done by the frictional force, which is equals to, okay, this is 0.46. This is 0.46. Then, okay, joules. Let's put joules. Then put this up also. So you have your 4 minus 40, because this is going to be -1. So if this is -1, this part here is -1. So if it's -1, we're going to have -40.6, -40.6 delta, which is our displacement. And then since we know that this is the only force that is acting on the object at the moment, so we can say the work net here is equal to the work done by the frictional force, which is gonna be 529.46 is equals to 40.6 delta. Divide, divide. Goes away, then you are left with something like this. Let's divide and see what we get. So we're gonna have 529.46 divided by 40.6. Then you'd have 13.04 meters, right? This is your distance that is covered. Okay, so that's how it looks. Now, final question before we close. 5.5. So the height of the track is now lowered so that point A is at a vertical height less than 3. Then the same crate is now released, right? So how will the distance now traveled by the crate along the horizontal surface before it reaches to rest compared to the distance calculated in the distance we just calculated? So this is logical. So here you see it's very steep, very steep. So what they're asking us, if let's say now we have box A here, then we'd have, if we lower this height to less than 3, then our path would be something like this, right? So you can see on a slide how this would slide. It would slide and then it would lose energy, maybe end up stopping here. But the more I make it more steeper like this, it can even go all the way to the end of the screen here, right? So that's what they're asking you. So the distance covered would be lesser here in this case compared to this one here because of the reasons I just said. So here, the more it's steep, it gains more momentum. So what happens is it's gonna have a high velocity. It's gonna fast. Then it's gonna cover more distance. But in this case here, it wouldn't, because it would go and then end up losing energy somewhere around here. Okay, that's how actually you would look at this. This one doesn't need a formula, it's more logical. Okay, cool, guys. Thank you. Thank you. Oh, you can even like use the mechanical energy actually, so you can do this. So here, if the height is no longer 3, then you'd have less potential energy here. So that means nothing is gonna be pushing this thing. Okay, cool, guys. Think that's it for today. Till we meet next time.